Think about your favorite Hollywood plot twist for a second. Maybe it's that chilling moment in The Sixth Sense when you finally realize the truth about Bruce Willis's character.
Oh, yeah, or perhaps it's the final frame of Christopher Nolan's Inception.
Yes, where that little metal top is just spinning and spinning.
And you are left just completely questioning reality itself.
Exactly. Those cinematic moments linger, because they totally upend the rules of the world you thought you were watching. But today, we are going to look at a twist that puts Hollywood completely to shame.
It really does.
Because today's twist does not happen on a soundstage. It happens at the atomic level.
Yeah.
And it literally bends the foundational rules of quantum reality. So, welcome to the show, the Deep Dive Lab.
It's a phenomenal topic to tackle today. You are fully justified in hyping up this twist, considering we're looking at a structural phenomenon that chemists and physicists have been theorizing about for decades,
Right.
but which most considered physically impossible to actually synthesize and stabilize.
So our mission for this deep dive is to unpack a profoundly mind-bending new research paper. It was recently published in the journal Science.
A fantastic paper.
Yeah, and we are looking at a newly engineered molecule that, well, according to standard traditional geometric rules, it simply should not exist in a stable form.
Not at all.
We are dealing with synthetic chemistry, advanced microscopy, and quantum computing all colliding at once.
The paper itself is spearheaded by lead author Igor Ronchevich alongside Fabian Paschke, Yuez Gao, and Leo Gross. And they are working with just a massive team of collaborators.
The institutional muscle behind this is staggering, honestly. We are talking about researchers from the University of Manchester, Oxford University, IBM Research Europe, IBM Quantum, ETH Zurich, EPFL, and the University of Regensburg.
When you see that level of cross-institutional collaboration, it's a clear signal that the research required incredibly diverse, highly specialized physical and computational tools.
It's basically an Avengers-level team-up of science.
That's actually a great way to put it. To really grasp the magnitude of what this team accomplished, we need to establish the baseline of normal molecular geometry for you, and then contrast that with the topological extremes they reached.
Let's ground this in a familiar visual. So
Yeah.
we all know the classic flat molecular rings, right? Like benzene.
Sure.
You can picture a standard circular Hot Wheels racetrack, just a simple flat loop of orange plastic sitting on the floor.
A classic.
Right. So a particle, or our toy car, goes around that track once, and it completes the 360-degree circuit,
Yep.
returning precisely to its origin point.
In chemical topology, that flat, untwisted ring geometry is referred to as a helical topology.
Helical topology, okay.
The conjugated pi electrons flow around the carbon ring in a straightforward, continuous plane. So the phase of the quantum wave function remains consistent throughout the entire orbit.
But we are not here to discuss flat tracks today. We are here to talk about topological twists.
The weird stuff.
Exactly. It actually brings to mind Tony Stark in Avengers Endgame.
Oh, in the kitchen.
Yes. He's in his kitchen trying to model the physics of time travel, and he tells his AI to render a Möbius strip. And while it makes for a great sci-fi movie moment, chemists have actually been synthesizing Möbius molecules for years now.
They have, yes. A Möbius strip is a topological structure created by taking a continuous loop, introducing a 180-degree half-twist, and then rejoining the ends.
So it possesses only one continuous surface and one continuous edge.
Precisely. If you place our imaginary Hot Wheels car on a Möbius track, a single orbit does not return it to the start.
Because it's on the bottom now.
Right. Because of that 180-degree inversion, the car or the electron must travel around the entire loop twice to return to its original quantum state and alignment.
So a flat Huckel loop requires one trip around. A Möbius strip with its 180-degree twist, or what the paper classifies as a generalized Möbius listing body, a GML 1/2 topology, requires two trips.
2 full trips.
But this massive team of scientists did not just build another Möbius strip. They engineered a molecule with half-Möbius topology.
And that is the absolute structural breakthrough at the core of this research. Instead of a 180-degree twist, this molecule exhibits a 90-degree twist.
Just 90 degrees.
Right. In formal topological terminology, it is a GML 1/4 topology. The 1/4 implies the twist is exactly 1/4 of a full 360-degree rotation.
The mathematical implication of a 90-degree twist is what really breaks down conventional spatial reasoning for me.
Oh, completely.
If a 180-degree twist requires two full orbits to reset the phase. A 90-degree twist dictates that a quantum particle traveling around this molecular ring has to circumnavigate it 4 times just to return to its original quantum state.
It has to pass through 1440 degrees of rotation.
That is just wild.
It really forces us to think beyond standard three-dimensional space and consider the extended phase space of the particle. The molecule itself is known chemically as C₁₃Cl₂.
C₁₃Cl₂.
Yes. As the formula indicates, it's an anti-aromatic ring composed of 13 carbon atoms with 2 chlorine atoms bonded to the periphery.
A 13-carbon ring is inherently fascinating because odd-numbered rings inevitably introduce structural and electronic tension. You can't simply alternate double and single bonds symmetrically around an odd number of atoms.
You really can't. That asymmetry is the foundational design principle here. The 2 chlorine atoms are attached at specific, highly strategic points along the carbon backbone.
So it's not even.
No, it divides the carbon ring into 2 unequal halves. One segment consists of 6 carbon-carbon bonds, and the other consists of 7 carbon-carbon bonds.
And that unevenness generates competing structural strains within the molecule itself. The carbon lattice desperately wants to planarize, to lay flat, to maximize the overlap of his pi orbital.
But it can't.
Right. The steric hindrance and the unequal bond pathways completely prevent it. This internal tension triggers what is known as the helical pseudo-Jahn effect.
The pseudo-Jahn effect is a brilliant piece of quantum mechanics. It essentially describes a situation where the symmetric, flat configuration of the molecule actually has overlapping ground and excited electronic states.
So it's unstable.
Exactly. To lower its overall energy and achieve stability, the molecule spontaneously breaks its own symmetry. The electronic clouds distort, forcing the physical carbon backbone to warp out of the plane, adopting that bizarre, highly specific 90-degree helical twist.
But knowing that a 13-carbon ring with 2 precisely placed chlorines will theoretically form a half-Möbius topology is one thing. Actually building it is an entirely different monumental challenge.
The synthesis is incredible.
Reading through the methodology, it evokes a microscopic, intensely high-stakes game of the board game operation.
Operation.
Yeah. You are maneuvering tiny tweezers, trying to extract specific pieces without disrupting the entire system.
The operation analogy holds up incredibly well, provided you scale it down to fractions of a nanometer and replace the tweezers with an atomic-scale electrical probe.
Just a slight upgrade.
Right. The synthesis strategy relied on a precursor molecule, C₁₃Cl₂. That's a 13-carbon ring fully saturated with 10 chlorine atoms on its exterior.
And crucially, they did not perform this in a standard chemical solution in a beaker.
No beakers here.
They deposited the C₁₃Cl₂ precursor onto an ultra-clean, atomically flat surface of sodium chloride, essentially a microscopic layer of table salt.
The salt acts as an insulating bilayer. It decouples the precursor molecule's delicate electronic states from the underlying metallic substrate of the microscope.
With the precursor isolated on the salt, they utilized a scanning tunneling microscope, or STM.
The STM features a metallic tip that tapers down to literally a single atom.
A single atom.
Yes. They position this tip mere angstroms above specific chlorine atoms on the precursor molecule. Instead of physical manipulation, they inject precise, localized voltage pulses.
It's localized, targeted electrochemistry. They fired voltage pulses ranging between 4.5 and 5 volts, utilizing a minuscule tunneling current of about 1 picoampere.
Basically microscopic lightning bolts.
Exactly. These lightning bolts provide just enough energy through inelastic electron tunneling to populate the anti-bonding orbitals of the carbon-chlorine bonds.
And this specific energy injection causes the targeted chlorine atom to detach as a radical or an ion, while the structural integrity of the underlying 13-carbon ring remains perfectly intact.
Through this meticulous atom-by-atom dissection, they cleaved exactly 8 chlorine atoms away, leaving behind the precise C₁₃Cl₂ structure.
The environmental controls required to achieve this are just staggering. This entire synthesis had to be conducted in ultra-high vacuum and at ultra-low cryogenic temperatures.
We're talking just a few degrees above absolute zero, right?
Precisely. Any thermal energy would cause the atoms to vibrate, which would blur the STM imaging and make targeted bond dissociation completely impossible.
It represents an absolute triumph of on-surface synthetic chemistry. But the researchers quickly discovered that C₁₃Cl₂ was not a static architectural marvel.
Not at all.
The molecule exhibits dynamic isomerism. It is effectively a shapeshifter.
A quantum shapeshifter.
This transitions the research from static architecture to functional mechanics. It behaves like an atomic scale transformer. It doesn't just sit there. It can actively alternate between distinct topological configurations.
The pseudo-Jahn Teller effect we discussed earlier creates a complex energy landscape for the molecule, featuring multiple stable minima.
Okay.
The researchers identified 3 distinct observable states for this single molecule. Using the STM tip, by tuning the voltage and injecting specific energetic electrons, they can reversibly drive the molecule over its activation barriers.
The first state is a left-handed half-twist. In quantum chemical terms, it's a non-planar open-shell singlet state. Let's call it the left twist.
Right.
By applying a highly controlled voltage pulse, they inject temporary energy, allowing the molecule to overcome the energy barrier and snap into a mirror image configuration.
The right-handed half twist.
Exactly. It acts as an atomic toggle switch, flipping between left-handed and right-handed chiral states.
But the phenomenon extends even further. By applying a different specific energy pulse, they can excite the molecule into a completely flat, non-twisted configuration.
And that flat configuration is the triplet state. Because the triplet state features 2 unpaired electrons occupying orthogonal orbitals, the repulsive electron interactions that originally drove the symmetry breaking are mitigated.
The internal tension relaxes.
The internal tension relaxes and the molecule reverts to that standard flat helical topology we visualized earlier with the Hot Wheels track.
The ability to reversibly cycle a single molecule through a left-twisting Half-Möbius singlet, a right-twisting Half-Möbius singlet, and a flat helical triplet using applied electric fields is completely unprecedented.
It's mind-blowing.
We are looking at an atomic switch that fundamentally alters its own topology and electronic properties on command.
However, validating that these structural transitions were actually occurring and mapping the exact energy required to trigger them push the absolute limits of modern computation.
They definitely couldn't simply rely on standard classical supercomputers for this.
The multi-reference character of the electrons in this molecule is notoriously difficult to model, isn't it?
Extremely. In classical density functional theory, or DFT, the algorithms typically assume a single dominant electronic configuration.
Right.
But in a highly strained twisting system like C₁₃Cl₂, multiple electronic configurations contribute heavily and simultaneously to the ground state. The electrons are highly entangled across that 90-degree spatial twist.
So a classical supercomputer, relying on binary ones and zeros, would require an exponential, practically impossible amount of memory to accurately simulate all those competing overlapping wave functions.
Exactly. To solve the quantum physics of this molecule, they had to employ an actual quantum computer.
They utilized an advanced quantum algorithm known as SQDRAFT, which stands for Stochastic Quantum Phase Drift.
It's a highly specialized protocol designed to calculate ground state energies on noisy quantum hardware by mitigating computational errors. And they executed this algorithm on a 72-qubit IBM quantum processor.
Running a simulation of this fidelity on a 72-qubit system places this research among the largest sample-based calculations ever executed on quantum hardware for quantum chemistry.
The researchers leveraged the inherent entanglement and superposition properties of the quantum processor to accurately mirror the entangled superimposed states of the Half-Möbius molecule.
It is a remarkable convergence of disciplines. Synthetic chemists built the molecule atom by atom, physicists mapped its topological states using advanced microscopy, and quantum computer scientists verified the underlying mechanics.
It's a beautiful synergy.
This leads us directly to the core question for you, the listener. We have unpacked GML topologies, pseudo-Jahn Teller's distortions, STM synthesis, and 72-qubit algorithms. It's a masterclass in pushing the boundaries of human knowledge. But what is the tangible, everyday relevance of C₁₃Cl₂?
Why does it matter?
Yeah. Why does a molecule that requires 4 loops to reset its quantum phase matter to the future of technology?
The significance lies in the boundary conditions of that 90-degree twist. Because an electron must travel 4 times around the ring to return to its initial state, it acquires a specific quantum phase shift, mathematically defined as a Berry phase of pi over 2.
A Berry phase of pi over 2 fundamentally alters how the molecule interacts with external forces.
It's essentially a unique electrical and magnetic fingerprint. Molecules with this specific topological signature are predicted to exhibit highly unusual responses to magnetic fields.
Furthermore, they demonstrate significant spin-orbit coupling.
Yes. The physical orbital movement of the electron around that twisted carbon lattice becomes strongly linked to the electron's intrinsic magnetic spin.
In a standard flat molecule, these properties are negligible. But in a half-Möbius molecule, they are massively amplified.
And because we already know the STM tip can switch the molecule on command between the flat triplet state and the twisted singlet states, we essentially have a mechanism to turn those amplified magnetic and electrical properties on and off at will.
We are looking at the foundational, atomic-scale Lego brick for next-generation hardware.
The applications are transformative. In the realm of quantum computing, these switchable topological molecules could serve as highly stable qubits.
Because of their topology.
Exactly. Their topological nature makes them inherently robust against local environmental noise, which is currently the biggest hurdle in quantum hardware development.
Beyond computing, this really paves the way for advanced, programmable, smart materials. If you can synthesize complex, macroscopic molecular networks utilizing these half-Möbius as building blocks, you could create fabrics, sensors, or microprocessors that drastically alter their physical shape, conductivity, or optical properties the very moment a specific electrical voltage is applied.
We are conceptualizing materials that adapt, respond, and process information based on geometric principles that, until this publication, were largely confined to theoretical mathematics.
As we synthesize the sheer volume of data we have covered today, let's distill this deep dive down to 3 critical takeaways for you. Number 1. Scientists successfully achieved the on-surface synthesis of a half-Möbius molecule, C₁₃Cl₂, by systematically plucking chlorine atoms off a precursor using a scanning tunneling microscope. They engineered a structure with a 90-degree quantum twist, requiring a particle to orbit 4 times to complete a single phase cycle.
Takeaway number 2. This molecule is dynamically switchable. Driven by the helical pseudo-Jahn effect, the researchers demonstrated the ability to use localized voltage pulses to toggle the molecule between a left-handed non-planar twist, a right-handed non-planar twist, and a completely flat Hückel ring. It functions as an atomic-scale topological switch.
And takeaway number 3, validating the multi-reference electronic structure of this shape-shifting molecule required unprecedented computational power. The team successfully utilized the SQD-IIFT algorithm on a 72-qubit IBM quantum processor, definitively proving that the frontiers of synthetic chemistry and quantum computing are now inextricably linked.
For a broader, big-picture takeaway, consider the historical context of materials science. For centuries, our technological progress has been dictated by the era of discovery.
We extracted iron, we isolated silicon.
Right. We utilized the molecular structures that nature provided. This research signifies that we have definitively crossed a threshold into a new era. We are no longer merely discovering materials. We are actively architecting swishable quantum molecules from the atoms up, bending the rules of geometry to design the building blocks of completely new technologies.
We are transitioning from finding our reality to actively designing its underlying source code. Thank you so much for joining us in the Deep Dive Lab today to explore this incredible convergence of chemistry and quantum physics. If you found this exploration of atomic engineering insightful, please subscribe to the channel so you never miss our deep dives into the bleeding edge of scientific research.
It's been a great discussion.
Before we wrap up, I want to leave you with one final lingering thought to mull over as you go about your day. We have established that scientists can now build and control individual molecules that act like atomic-scale transformers, utilizing complex, multidimensional loops to shift their physical and electrical shape on command. What happens when we develop the capability to seamlessly link millions of these topological switches together into a coherent lattice? How will macroscopic materials that can literally change their quantum geometry on the fly revolutionize the computational devices sitting in your pocket right now? Keep questioning the limits of what is possible. We will see you next time.